Welcome. This is Fundamentals of Micro and Nanofabrication. I am Shobhan Awasthi from IIT Bangalore. This starts the module on chemical vapor deposition. But before we get into the nitty-gritty of the technique itself, I would like to take a little detour and explain some of the definitions and terminology that we will use in the rest of this module. So, there are two types of depositions that you can theoretically do. One uses chemical vapors and one uses physical vapors. In chemical vapor, the idea is that you do not have the material that you are depositing completely fabricated yet. So, what you have is just the precursor. So, supposing you are depositing silicon dioxide, then you would flow a precursor of silicon and you would flow a precursor of oxygen and actually do the reaction at the wafer to form silicon dioxide. In physical vapor deposition, you already have the silicon dioxide pre-made either in a solid state form or in a pellet form or in a powder form, and then you figure out a way to transport this already formed silicon dioxide from your source to your substrate. In general, chemical vapor deposition gives slightly better quality, which is why it is used for semiconductor deposition, while physical vapor deposition tends to be cheaper, simpler, and is often used for metal and dielectric depositions, a non-critical deposition, if I may say so. So, this is the module that we are going to first take, which is chemical vapor deposition, and after CVD we will then discuss physical vapor deposition. So, before that, let us get some of the terminology right. So, there is this concept of uniformity. So, you may have certain notion of what uniformity means, but let us standardize the definition a little bit more carefully. So, in deposition, uniformity refers to the fact that how does your thickness change over your wafer. This is important because after deposition you often have an etching step. So, here is an example. So, you have taken silicon and you have deposited silicon dioxide of some thickness, but because of some problem your silicon dioxide was not uniform. So, it was thinner on the left hand side, thicker on the right hand side, and after that you did some etching. So, that etching recipe was probably optimized by somebody assuming that the silicon dioxide wafer silicon dioxide thickness is uniform. So, they gave you a recipe that would work just right if the silicon dioxide thickness was also just right. However, in some places the thickness is lower. In those cases you would over etch the sample, so the opening would be larger than expected, and in some cases you would under etch the sample because in which case you would do not have the opening at all because the silicon dioxide was thicker. So, these sort of problems can only be avoided by having the silicon dioxide uniformity to be very precise. So, you should aim to have uniform deposition everywhere. The second concept is of conformality. So, conformality means that you follow the underlying topology. So, best explained by a figure again. So, here is a silicon. Supposing you have silicon dioxide on top and that silicon dioxide is patterned, and now you are going to deposit metal on top. So, now that metal can have a conformal coverage, and conformal coverage it basically maintains the thickness no matter what the underlying topology is. So, the thickness is consistent across this whole topology. Practically you may not get this. So, let me grab my laser pointer. Practically you may not get this. You may see that over sharp corners the deposition is a little more thin, and when the deposition is a little more thin, then the thickness is not exactly the same all the way through. It is thinner here than it is there. So, this is what is called a good or a perfect conformal coverage. This would be called a suboptimal or poor conformal coverage. Conformality can sometimes be important. It really depends upon your application. Sometimes it is not. But it is a good idea to always know in advance whether the process that you are using will lead to conformal deposition or not. A related concept is one of step coverage. So, often in papers and in processings you will hear this word step coverage. What it basically means is whether the film deposition is conformal or not. So, again here is your wafer surface and you have a step because you have deposited something and then patterned it, and then the question is that this black layer that you are depositing on top, is it following this step exactly or not? So, if it is following this step exactly, then you have a good step coverage. If it is not exactly following this step and you have a thinner deposition here, then it is poor or bad step coverage. A little bit of introduction into gas or fluid flow would also be important to understand chemical vapor deposition a little. So, whenever a fluid is traveling in a constrained medium, say a tube, a pipe or a reactor, it tends to follow the laws of fluid dynamics. Now, here the fluid is can be either liquid or gas. Of course, in chemical vapor deposition, we are primarily looking at gas. The actual physics of fluid flow is fairly complicated. So, in order to simplify things, we typically look at 3 classes of flow. So, one is called the molecular flow. This is what happens when the particles or molecules are so rare that they do not collide with each other. So, they don't know of each other's presence. In that case, the only thing that the molecule or particle interacts with is the physical container itself. So, that can be a pipe, a wall, a chamber, etc. In these cases, the flow is actually not proportional to the pressure drop across this pipe. So, simply because if you have a pressure gradient does not necessarily mean the flow will scale with that pressure. This is the case that happens in vacuum chambers. Right? So, if you have a vacuum chamber and very low pressure, then you are in a molecular flow regime. The more familiar to you may be the laminar flow regime, which is often discussed in introductory physics courses, where you must have seen Bernoulli principle, you must have heard of Navier-Strauss equations, etc. So, that they all tend to define the laminar flow. So, in this case, the particles collide with each other, but the flow is streamlined. So, the particles tend to maintain these streams, right. So, that is what the laminar flow means. So, this particle will flow sort of parallel to other particles and along the shape of the tube. This occurs at low Reynolds numbers and the flow is proportional to the pressure. So, depending on the amount of mass transfer from left to right will depend upon how much pressure you apply from left versus right. And the third and the most complicated case is actually the turbulent flow, where the flow velocity becomes so high that the particles collide with each other so much that they are not streamlined anymore. The physics of this is fairly complicated. It typically occurs at high Reynolds numbers. These two regimes are what are called viscous flow regimes and they are typically present in a CVD reactor. By and large, in practical CVD reactors, we tend to maintain laminar flow. Why? It will be obvious in a minute. So, which regime we are in would depend upon the pressure of the tube, the amount of the pressure which tells you the density of the gas. It depends upon the tube diameter, the reactor diameter, the pressure you have across it, the flow rate, viscosity, density. Cumulatively, all of this is captured in 2 numbers. One is called the Knudsen number and one is called the Reynolds number. And if depending upon what those numbers are, you are either in the viscous flow regime, which is laminar or turbulent, or you are in the molecular flow regime, or you are somewhere in the middle. So, for CVD, you tend to be in this region above this red curve in the viscous flow regime. In order to maintain laminar flow, the Reynolds number must be 2000, which leads to the question, what is the Reynolds number? I will not quiz you on this, but just for your information, Reynolds number is simply a unitless quantity which is given here, which basically tells you how fast the fluid is flowing through your tube, right? And if it is flowing too fast, then the flow becomes turbulent, which is bad. Typically, you get laminar flow for Reynolds numbers less than 1000 and you get turbulence for Reynolds number about 2000 or so. So, here are some numbers for hydrogen at various temperatures. One thing to notice is that for a very large range of temperatures, the viscosity and the density do not change much. So, that is good news. That means is that if you design a CVD reactor that is laminar 700 degrees C, there is a good chance that it is also laminar around 1200 degrees C. So, the variation of temperature does not change the fluid dynamics of too much. Now, the reason the CVD regime tries to remain in the laminar flow is highlighted in this slide. So, if you are in the molecular flow regime, typically your density is very low, your pressure drop and flow rates are very small, which means your growth rates are very small, which is impractical and you do not want to do that. However, if you are at the turbulent flow regime, even though you have a lot of pressure drop, you have a lot of flow rate, you have a lot of material going through, the growth is very unpredictable. It's very it's too unrepeatable, and if it's too unrepeatable, it's not a good microfabrication process. So, by and large, most CVD reactors try to stick to the laminar flow regime, where the growth is both predictable and reasonably high. Now, before we go further, let's take a look at how laminar flow happens inside a pipe. So, if you have some liquid flowing through a pipe, you must have some pressure difference. So, you must have a region of high pressure and a region of low pressure, and this is creating the gradient that is pushing the fluid from left to right. Now, as this fluid goes through this pipe, and if this is a viscous liquid, then it would have a certain velocity profile. Under no slip conditions, you assume that the velocity at the interface is essentially 0, and then that velocity profile increases, and then it again falls as it reaches the other interface. So, this is imagine you are looking at the cross section of a tube with a diameter of a radius r, right. So, the velocity is lower at the interface with the tube, and the velocity is highest somewhere in the middle. And the reason for this velocity profile is because this liquid is viscous. So, it has some friction, it interacts with the other particles or other molecules, and hence maintains this profile. Now, the viscous flow is given by this equation, the force due to pressure is given by this equation, and under equilibrium they are both equal, which gives you the profile of this velocity as a function of its radial position, as a function of the polar coordinate. Now, Poiseuille's law basically says that the amount of flow that you are getting is nothing but velocity multiplied by this area. Now, since this velocity is non-uniform, you must do some calculus to actually calculate the integral of this flow as a function of radius and pressure. And if you do all this calculation, which is simple calculus, you actually see that the total flow in this pipe is equal to the pressure drop multiplied by a constant, and this constant is nothing but it consists of geometric factors, right? Geometric factors and viscous force. This equation is very similar to the equation that you see of current flowing in a resistor, which is that the flow current I must be equal to conductance, which is 1 over R, where R is resistance, into pressure drop. Here the pressure drop is just analogous to voltage drop. So, in some sense this is nothing very brilliant, this is simply an Ohm's law, but for gas flow. So, now what you are looking at is, instead of current you are looking at mass flow, instead of voltage you are looking at pressure drop, and this value represents conductance, which is not electrical conductance but conductance of fluid flow. So, this is sort of an important insight, because what this allows you to do is to understand that when you are doing a design of a CVD reactor or analyzing the working of a CVD reactor, it can be thought of as a simple electrical network problem, where every component has a certain conductance, has a certain conductance, and you can think of mass flow controllers as current sources, you can think of pumps as grounds, etc., etc. So, the design of any vacuum system, not just CVD equipment, but any vacuum system, can often be just thought of as series of conductances either in parallel or a network of conductances either in series or parallel. And the trick to understanding how much gas would flow would be to know what is the pressure drop across the system and what is the effective conductance. And the effective conductance follows the same rules that you know from series and parallel combinations of electrical resistances. So, in series the conductances are inversely added, in parallel the conductances are simply added. Now, in a real system you do not necessarily build a system that is conductance limited. Let me explain by giving a practical example. So, supposing you took if you take your house, right, and your house you have a fan. Now, in order to control the amount of current that flows through that fan, you do not calculate an effective resistance and then use a wire of precisely that resistance, right. That is not what you do. And the reason you do not do that is because it is too unpredictable, it takes too much work. Much simpler is to connect the fan through a regulator, and this regulator has some knobs, and depending upon what is the setting of this knob, you actually control the current. So, you do not give a precise value of conductance of this wire, you just put a wire with a very large conductance and in series add a regulator which can tune the conductance. In practical vacuum systems you do the same thing. So, you do not plan the conductance of your whole system, you just apply very thick pipes which can conduct a lot of fluid. but somewhere in the middle you put a regulator. Now, that regulator for gas flow can either be a pressure regulator, it can be a mass flow controller, and this is what actually controls the flow of the gas through this system. And on the other hand, you have a pump, and pump can be thought of as nothing but something that basically creates zero pressure, which is equivalent to a ground, right. So, in this manner you can actually analyze any complicated reactor to actually understand how the gas flow works. Of course, reality is a little more complicated. CVD design is a fairly challenging problem, and there are a lot of second order effects to consider, a lot of computational fluid dynamics etc. used. We will not go into any of those details because that is far too advanced for this course. I will just leave you with this generic idea that I introduced, which is that when you are analyzing vacuum system, when you are analyzing fluid flow, it is often useful to think of pumps as essentially power supplies, things that create voltage gradients, things that create voltage differences. So, tanks and pumps, gas cylinders and pumps are nothing but something that creates high voltage and something that creates low voltage. The conductance of wires can often be thought of as, the conductance of the tubes can often be thought of as the conductance of wires in an electrical circuit. Mass flow controllers, pressure regulators can often be thought of as simple ways of regulating the current in the circuit. And just like there is Ohm's law for electrical circuits, there is a similar law for gas flow in a fluid medium when it is under laminar flow regime. So, that is enough for this lecture. In the next lecture, we get into more details of how CVD works.